Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. We are looking at the phenomenon of diffraction since the last module because we have discussed the importance of diffraction already, right. So, at the end of the module we were making certain assumptions in order to understand the mathematical expressions which you will soon see that they are not that difficult. Of course, the process of arriving at them is very difficult, so we have not attempted to do that one, but the basic idea is kind of intuitively understandable that the field that is generated from the spherical wave at the source point P or one of the parts of the source would propagate all the way to the point Q on the aperture, and at point Q you would then again have a spherical wave which would propagate to psi of P prime. Okay. And the field from P not only goes to Q, it goes to all other points on the aperture, right. So, it goes to all other points of aperture and each aperture will have a small area around it, and then you will have to look at the field strength at different points on the aperture which would all be propagating to the point P, and at that point P you have to sum up all the contributions from the different parts of the aperture. Okay. That is what Huygens principle is, and that is what mathematically we are going to just write it down. We already have made one assumption in the sense that the distances r, r0, s, s0 are very far away from the aperture, and we call this as the Fraunhofer diffraction or the Fraunhofer limit of diffraction. Okay. The second assumption that we make is that the field that you are going to get on point Q on the aperture because of the point P on the source side would actually be, that would just be that, in the sense that I have an aperture, the aperture could actually modify the field that is coming in, right. So, the field is coming far away from this distance r, almost incident in the form of a plane wave, and this field could actually be modified here. Why would it be modified? Because this aperture is surrounded by the opaque material. So, these are these materials, and the edge effects may actually transmit some of the light that is falling on the edge onto that and modify the field pattern in the aperture plane itself. Okay. This is usually considered by what is called as the transmittance function of the aperture. What we are going to do is that we will assume the transmittance function which would be dependent on lambda, which would be dependent on the precise location of the aperture point that we are considering, that is point Q on the aperture that we are considering. All those things we will assume that this transmission function is actually equal to 1. Okay. This is an assumption that we are making, but it is a very good assumption to make because it simplifies our life in many ways. So, following this basic idea, first what would be the field at point Q due to point P, that is source at point P? This would be some psi 0 divided by r e to the power minus j k r, where r is the distance between source point P and the aperture point Q, correct. This is the spherical wave which we already have seen earlier. Now, what is r? We know that r is basically the distance PQ, and we know that the coordinates of P and Q are given by P coordinate is basically xs, ys and zs, right, and the Q coordinates are x0, y0 and 0, because we have assumed that this is located at z equal to 0 plane, then these are the coordinates that we actually have, right. So, what would be the distance PQ? Remember, I am only interested in the distance, right. This would be xs minus x0 whole square plus ys minus y0 whole square plus zs square under root, correct. Now, what is the distance r0 itself? R0 is the distance from the point P to the origin. Origin of course is given by 0 0 0. So, the distance from P to 0 is given by square root of xs square ys square plus zs square, right. Now, we can expand this distance PQ, okay. We can expand this distance PQ or this value r, and then write this as xs square plus you will have x0 square minus 2 xs x naught plus ys square plus y0 square minus 2 ys y naught plus zs square under root. Clearly utilizing the fact that r0 is given by this particular expression, what will I have? Xs square, I can take this. I can take this ys square and zs square and call this entire thing as r0 square. Then I have x0 square plus y0 square. Then I have x0 square plus y0 square is kind of given by the radius. So, if it was a completely spherical aperture, then x0 square plus y0 square would essentially be telling us the area of a circle, right. So, that would sorry, the radius of the circle, and as you change x0 y0 go to other points on the aperture, eventually this is going to cover the aperture area, right. So, this is x0 plus y0 square. In other words, you can also think of the point Q and from the origin to the point Q, and this distance can be given as x0 square plus y0 square under root, because Q is given by the coordinates x0, y0 and 0. So, that is all that this particular part is, and of course, the length of this arrow can become equal to the radius of the aperture, assuming a spherical aperture when the point Q lies on the edge of the aperture, right. So, that is all this particular thing is. Then you have inner product of this xs and x0. So, you have minus 2 xs x naught plus ys y naught. Okay. So, this is what you have, entire thing under root. Now, we are going to make some assumptions. We are going to assume that this r0 square is much larger than any of these two terms. We are justified in this assumption. We have already said this. We are working in the Fraunhofer diffraction limit. In the Fraunhofer diffraction limit, the distance from the source to the aperture and from aperture to this one itself is very large compared to the dimensions of the aperture. Okay. So, because of that, I can take this r0 out of this square root, and then I will get these two terms to be divided by r0, and then I am going to just write this out as approximately r0 into 1 plus x0 square plus y0 square divided by 2 r0 square minus xs x naught plus ys y naught divided by so the 2 will cancel. So, you can show this as a simple exercise. You are going to get this as r0 square, or taking r0 into inside the integral, or sorry, inside the brackets, I can remove one r0 down here, and then what I will get is this term. Okay. So, I will have r0 plus x0 square plus y0 square by 2 r0 and this quantity. So, further in the Fraunhofer limit I can neglect this. Okay. Why could I neglect this? Well, this is the Fraunhofer limit, and r0, which is the distance PO, will be very large compared to x0 square plus y0 square. So, now with that I can remove this term, but we will see that this term needs to be included later on. At that point we will include. Okay. For now we are going to neglect this because we are working in the Fraunhofer diffraction limit. Okay. So, this is what you are going to get in terms of r. So, in the denominator for e power minus j k r by r, what I can do is to further approximate the denominator as 1 over r naught, because you see you are again making this similar approximation that we had made in antenna analysis as well, right. There also we had an e power minus j k r, and in the denominator we had an r. There we made this kind of an assumption. Okay. This assumption is sometimes called as paraxial assumption. So, especially in the context of diffraction, and that is what we are actually making now. We assume that this is 1 by r naught in the denominator, and in the numerator we will write down this approximation. Okay. So, I can't make in the numerator the approximation to be equal to r is equal to r naught. I can make that approximation in the denominator because a small deviation about r0 would not be too much change in the amplitude of the spherical wave. Okay. So, now in the numerator I will have e power minus j k r0, then I will have, this is a minus sign. Okay. So, I will have e power j k xs x0 plus ys y0 divided by r0. Okay. So, please note this particular expression. This is, if you multiply this entire thing by size 0, this expression would be the the field light that is incident at from the point P and now incident at point Q. Okay. And when you multiply this one by d sigma, this would correspond to the contribution of the wave or the aperture point Q with a cross section d sigma onto the observation plane P or P prime. Okay. So, please note that. So, psi of Q times d sigma is my contribution onto the field point P prime. Okay. So, that is what this particular thing is. However, this is the amplitude of the field that is being incident. This further needs to be multiplied by another spherical wave, right, because this amplitude would now be the input amplitude kind of a thing, which would then begin to propagate as a spherical wave all the way to the field point at P prime. P prime is located at the coordinates x, y and z. So, similarly to the assumptions that we have made, you can show that the distance OP prime can be written as in the denominator as it can be written as 1 by S0, or rather in fact OP prime is not that one. OP prime is basically S0, which is given by x square plus y square plus z square under root, and utilizing this x square plus y square under z square defined as S0, you can then show that p prime to q, or rather q prime to p distance, which we have denoted as S, can be approximated as S naught minus, okay, this would be x 0 x plus y 0 y divided by sorry, I think, yeah. So, this is divided by r, sorry, not r 0, this would be S 0, right, because I am actually looking at this one. So, I can make this approximation. I can do this based on whatever we have already discussed. In the denominator, we are going to make the approximation that S will be approximately S naught in the denominator, and in the numerator or in the phase factor expression, we are going to retain this approximation, okay, this same paraxial approximation. So, with this as the amplitude, the next part of the spherical wave would be given by e power minus j k S naught, right. I am just following the same ideas that I have already written down. So, there will be 1 by S 0 e power minus j k S naught. You can observe that these terms are essentially the same as we have written earlier, times there will be this additional phase factor, which would be e power j k x 0 x by S 0 and plus y 0 y, this entire thing divided by S naught, right. So, this would be present. So, the field, differential field that you are going to get, at the point P prime, which is the field point, okay, would be given by psi 0 divided by r 0 S 0, which of course would tell you the overall amplitude clearly, because you had propagated a distance up to 1 over r 0 and then another distance of 1 over S 0. Yeah, you would expect that this would actually be like 1 by r 0 plus S 0, but it turns out that because of this contributions that you are going to get slightly different, you will have to start the spherical wave, reach q, and from q you have to count the next part of the spherical wave, right. So, that is why you have psi 0 by r 0 into S 0, not r 0 plus S 0. Okay. So, this part is anyway understood. The overall phase that you are going to see would be e power minus j k S 0 plus r 0. This is now understandable, because as you move a distance of r 0 to begin with, you would have changed the phase by e power minus j k 0, or rather k r naught, and then moving an additional distance of S 0 would have changed the phase to k S 0, and therefore, the sum of the phase would be the one that would actually determine the overall phase. So, this is e power minus j k S 0 plus S 0, and then you have these two phase factors to go with. Now, you can return to the case that we considered earlier, that is, we will assume that the source is located on the axis. Okay. So, for an on axis source, x s will be equal to 0, similarly y s is equal to 0, because the source is now located at the point z s, right, it is on the axis. So, when you make this assumption, this point source assumption further, then you can drop the phase term that is appearing here. So, I can drop this phase term, and whatever the phase term that I would be left with only be this, and knowing that k is given by 2 pi by lambda, I am going to write down the phase term slightly differently. I am going to write this as 2 pi x by lambda S 0 times x naught plus y by lambda S 0 by y naught. Please note the variables that I have grouped here. I have now fixed my field point to point P prime. Of course, sorry, this is the part that we have written, right. Yeah. So, this is the differential amount. I need to also multiply this one by the cross sectional area d sigma that we were considering at the aperture point. So, this is the differential field that I am going to get, and what I have now seen is that there is an overall phase factor acceptable, there is an overall attenuation factor which is 1 over r 0 S 0, which is also acceptable, and the initial amplitude size 0, and there is an extra phase shift that we have obtained, which I have put in here. This other phase shift that I have neglected, will actually be, we need to include that phase factor when we go to what is called as Fresnel diffraction limit. Okay. So far it is not necessary that we need to include, not this term, the quadratic term. This term which we have neglected now is because of the on axis field. So, if your field is not on axis, then you have to include this particular term. Okay. And as I have said, we have nowhere indicated the orientation. So, we have assumed that all the obliqueness is actually not there, everything is kind of collinear, which of course we realize is not true, but this assumption makes our life little easier in terms of getting the expression. So, I am going to use this. Of course, this is just the differential point at p prime, the contribution from point q. What if I start moving q around the aperture? Every point should contribute to the field at point p prime, right. So, when you do that, you know that instead of considering the field at that point as a differential point, you simply have to integrate over the aperture distribution. Okay. Please note the aperture is actually described according to the coordinates x0 and y0. Okay. So, not x and y are not your variables, they are kind of fixed here, x0 y0 is the variable that is moving, and you have to simply integrate this one over d sigma. D sigma itself is given by dx0 dy0. Okay. This expression that we have, what you can observe that is that this S0 and R0 are kind of independent of x0 and y0, right. The distances that p prime q as well as the distance p q are independent of this dx0 dy0. Similarly, if you assume that psi 0 is a constant and this r0 x0 is also independent, then you can actually move these outside the integrals. Okay. So, you can move this outside the integrals and then integrate this factor over the aperture distribution. Okay. So, whatever the aperture shape that you have is being integrated. If you are not happy with this integration over the aperture, you can make the integration go to minus infinity to plus infinity, and then you call this as aperture function of x0 and y0, right. So, if you call this as aperture function of x0 y0, that would tell you how the aperture itself is distributed, and the integration could be minus infinity to plus infinity, which is also okay. I mean, we can also do this, and then you have this e power j 2 pi. I am going to write this as kx, or rather fx x naught plus fy y naught. Okay. And then I have dx naught and dy naught. For those who have seen Fourier series and Fourier transforms, you can clearly see that this is the Fourier synthesis equation, right. Given the aperture as a function of x0 and y0, if you take the Fourier transform of this aperture function, what you are going to get would be the complex field that is the field that you are going to get at that particular point p. Okay. And fx and fy are clearly given by, fx is given by x by lambda s naught and fy is given by y by lambda s naught. One final assumption that we are going to make is that this distance from on the aperture that you had, right. So, this was the origin of the aperture, this was s naught and this was s, and this aperture was located in the plane z, right. So, what we are going to assume is that this aperture itself is so small that S0 can be approximated to the value of z itself. Okay. So, I can remove this S naught, which would give me the distance from the origin, but rather I can just put it in terms of the plane distance itself, which would be x by lambda z and y by lambda z. So, clearly this is a wave, I mean this is similar to a frequency, except that this is called as a wave number. Okay. So, this is the Fourier transform, or rather if you are that not happy with the sign, then this is the inverse Fourier transform of the aperture x0 y0. So, in order to calculate the field at the point P, if you neglect all these constant phase factors, and if you also assume that this thing is very well known, this 1 by r0 s0, then what you have is the inverse Fourier transform of the aperture. Okay. This gives us a nice starting point for understanding diffraction from different apertures. Before we go to that, we can slightly more rigorously consider what have we neglected and what is the assumption that we have made. We have made this assumption, right. So, we said r0 square is much larger than x0 square plus y0 square. Actually, when you take the binomial theorem, then what we would have said is that so the term that you would have obtained and neglected is x0 square plus y0 square divided by 2 r0 square, right. So, this was neglected in comparison with r0 itself, which we had taken out. So, or no, this would be neglected with respect to 1, because this is the one that is going to give us the phase. right. So, we neglected this component, we neglected this after multiplying by r. So, we said this is 2 r 0, but then after multiplying by r 0, which was actually coming in from that other side, we had to take out this r 0 on both sides. So, this is the part that we said, and this one was considered to be very small compared to 1. Equivalently, what we have here is that if you think of this x 0 square plus y 0 square, what is the maximum value of this numerator term? The maximum value of this numerator term would be the distance that you are going to have, right. So, that would be some a square, where a is the radius of the aperture, right. So, what you have is a square divided by 2 r 0 to be much less than 1. So, a square by 2 is much less than r 0. So, this is the condition that we actually had. Okay. Of course, there is a factor of lambda involved. What I will do is I will give you the correct expression. The correct expression is pi a square by lambda is considered to be much smaller than the. So, instead of r 0, we have to of course consider the s 0, because r 0 is usually considered to be so far away that we assume this is a plane wave, right. So, this is pi a square by lambda should be much less than s 0, as you can actually obtain from the expression for s 0. Okay. So, I will develop this one more clearly in the exercise. And then I will also tell you what the implications of not having to satisfy this equation. For now, we know that if I am given an aperture function in the form of aperture at x 0 y 0 located at the plane z equal to 0, the aperture is located there. If you take the inverse Fourier transform, then what you are going to get will be a function phi k x and k y, of course, or rather phi f x and f y. Of course, f x is equal to x by lambda z, f y is equal to y by lambda z. So, you are actually getting this in terms of the x and y coordinates itself. Okay. So, this is the inverse Fourier transform expression. Now, let us look at two important cases. Okay. First, I am going to consider a rectangular aperture. Okay. So, I will assume that the aperture has a width of w x along the x direction and w y along the y direction. So, this is y, this is x. So, this is like taking a cardboard and cutting a rectangle out of it. The rectangle is defined by the dimensions w x and w y along the x and y directions, and we want to understand what is the inverse Fourier transform of this. Now, you might not have seen the two-dimensional Fourier transforms, but in this particular case you can actually split the two-dimensional Fourier transforms into two products of two single-sided Fourier transforms, one acting along x 0, the other one acting along y 0, okay, or rather x and y. So, this aperture function that we have, which we have defined to have an amplitude of 1 here and 0 everywhere else, can be expressed mathematically as rectangular function of x 0 by w x multiplied by rectangular function of y 0 by w y, and only in this Cartesian coordinate system, in this particular example, you can split the two-dimensional Fourier transform into product of two one-dimensional Fourier transforms. And knowing very well from your classes on signal systems or Fourier transforms, this rectangular function in one of the variables will actually turn out to be a sinc pulse in the complementary variable, right. So, the expression would be w x sinc of f x w x, right, and you know what is f x? F x is x by lambda this thing. So, therefore, for the x part this would be w x sinc of x w x by lambda z. Okay. So, this is the expression that you are going to get. Similarly, the rectangular function along the y direction would give you w y sinc of f y w y, okay, and this fellow can be written as w y sinc of y w y divided by lambda z. Okay. So, this is all in terms of f x and f y being replaced in terms of x and y. So, overall will be the product of these two, okay. And if you sketch what you are going to get in terms of x and y, actually you can use MATLAB which would to give you a 2D graph for this. So, you just define, so imagine that w x is given by 1, w y is given by 2, and then you can write down a simple MATLAB script in order to see what the two-dimensional distribution would be. Of course, one-dimensional distribution is very well known to you, right. So, this is a sinc pulse distribution. So, if you take the argument of the sinc pulse as f x, and of course, you will also have another sinc pulse, okay, which would be along the y direction. So, I am going to write this one. So, it would actually be a two-dimensional sinc pulse that I have written here. For clarity, I have shown it in two different axes. And where does the minima occur? Remember, what we are looking for is a sinc pulse, and sinc pulse will actually have a minima at Fx equals 1 by Wx, right, but Fx we have already written it as here. So, it would actually have unity at say x by lambda z equals 1 by Wx, or at the spatial location on the field point at x is equal to lambda z by Wx. So, if you fix the value of z, you know what distance that you are looking at, then the width Wx will move the 0 on the x axis, right. So, on the x axis where the 0 occurs will be determined by what the width Wx is. Similarly, you will get when Fy is equal to 1 by Wy, this will be the first side lobes, right. So, the first points where you are going to get to zeros. Of course, the integral multiple of this will actually give you higher zeros as well, but as you can clearly see where at point your optical field is going to 0 can be controlled by the aperture Wx and W0, right. So, in a 2-dimensional thing you will actually see a central bright spot, then there will be these rings, you know, around this. This is what you are going to see in a 2-dimensional plane if you actually do it nicely. Another thing that you can do is to consider diffraction by a slit. Okay, this slit is the one that would correspond to the small aperture thing that I actually talked about. What you can now assume is that if the slit is along x axis, then you can take Wx to be much larger than Wy. Okay. So, when you do this one, what you are essentially making is this sink of Fy Wy with Wy tending almost to 0 can be approximately equal to 1. So, then you do not really get any variations in the y plane, you will get variations in the x plane. So, if you put up a screen along x, you will see minima, slight maxima, minima, maxima, minima, there is a main lobe maxima, and then it goes on that way, right. So, this is the sink pulse. Please keep the expression of slit in mind, because we are going to use this for another phenomena called as interference. In fact, we can describe interference using diffraction. Of course, that is not how historically it was obtained to begin with. Historically, what was obtained was interference and then diffraction to show the wave nature, but we will look at it as a interesting and amusing exercise in the next module. Okay. Finally, we mentioned the circular aperture, and in this circular aperture, which would be like an aperture of size a or the radius a, unfortunately the corresponding expressions are not so straightforward. In fact, you can show that there will be a central bright spot. This is sometimes called as Poisson spot, or sometimes and first discovered or first realized experimentally by a person called as Arago. Okay. So, sometimes it is also called as Arago spot, but this is also called as not Poisson's ratio, I am sorry, this is called as Poisson spot. Okay. And there is an interesting bit of history behind this, which we will not be able to tell you, but you can look up Wikipedia for this. So, there will be central bright spot followed by these many rings. Okay. In fact, these rings are known as Fresnel zone plates. We will meet these Fresnel zone plates later on, and what you can see is that the diameter of this disc, okay, which we will call as airy disc sometimes. So, this diameter is roughly, I mean, it is inversely proportional to the aperture area, and an exact expression for circular aperture, the field will be Bessel functions, and unlike the rectangular aperture, we can't separate the 2-dimensional Fourier transforms, and taking 2-dimensional Fourier transforms in the circular or the cylindrical coordinate or the spherical coordinates is kind of difficult. So, I am not going to cover that, but you have to understand that if a point source is present, what you get at the field or the screen point is not just a point, but actually a disc of certain aperture, which is about 1.22 Wa divided by something like that. Okay. So, these expressions I will look at, I mean I will give you in the exercises for you to work on, and you can use MATLAB in fact to a great extent to understand these diffraction problems. Our study of diffraction is not complete yet, because we are going to next consider Fresnel diffraction, which will be much more important for us to understand the wave bending nature and what is the effect of that on the wireless channel attenuation. Thank you very much.